Solving Rational Inequality, Quarter 1, Module 6. In plotting the critical values of the rational inequality, always check the inequality used and consider the following. If the inequality is less than or greater than, we will use an open circle. In plotting an open circle, it means that the value is not included to the solution set. If we will use the inequality less than or equal or greater than or equal, we will use a closed circle. So it means that the value is included to the solution set. Examples. In the given interval -3 is less than x but x is less than 5, it means that -3 and 5 are not included to the values of x. In plotting this in a real number line, so let us start with -3. So you have observed that we use the inequality less than. So we will use an open circle. It means -3 is not included to the set of values of x. Next, we have 5. So since the inequality is less than, so we will still use an open circle. So it means that 5 is not included to the set of values of x. Next interval, we have -5 is less than x, but x is less than or equal to 4. It means that -5 is not included, but 4 is included to the values of x. In plotting this in a real number line, so let us start with -5. So since the inequality is less than, so we will now use an open circle. And we have also 4. You have observed that the inequality is less than or equal. Therefore, we will use a closed circle. So it means that -5 is not included since it is an open circle. +4 is included because it is a closed circle. Next interval, we have -8 is less than or equal to x, but x is less than 3. It means that -8 is included to the values of x, but 3 is not included to the values of x. In plotting this in a real number line, so let us start with -8. So since the inequality is less than or equal, we will use a closed circle. Then we have also 3. Then you have observed that we use the inequality less than. So we will use an open circle. So you have observed that -8 is a closed circle. It means it is included. While 3 is an open circle, it means that it is not included to the values of x. The next interval, we have -2 is less than or equal to x, but x is less than or equal to 7. It means that -2 and +7 are included to the values of x. In plotting this in a real number line, so let us start with -2. So since the inequality is less than or equal, it means that we will use a closed circle. We have also +7. Since the inequality is less than or equal, we will use a closed circle. So you have observed that in the given set of values in a real number line, -2 and +7 are included to the values of x. Steps in solving rational inequality. Step 1. Write the inequality in the correct form or general form. One side must be 0 and the other side can have only one fraction. So simplify the fractions if there is more than one fraction. Step 2. Find the critical values. Set the numerator and denominator of the fraction equal to 0 to find the critical values. Step 3. Plot the critical values in a real number line. use open circle or closed circle depends on the inequality used for the numerator. Note, all the critical values of the denominator must be plotted in open circle. Again, the denominator must be plotted in open circle. Step 4. Write the set notation form of each interval in a real number line. Step 5. Test each interval using the value of x. If it is satisfied to the given inequality, if the value of x on the interval is 2, then it is the solution set. Otherwise, if it is false, and then it is not a solution set. Note, do not use the critical values as your testing values. Step number 6. Write the set notation that satisfy to the rational inequality. If there are two or more sets that satisfy, use union, or the word or, it means to combine the solution sets. Solve the inequality 2x over x plus 1 is greater than or equal to 1. Step 1. We need to write the given inequality, this inequality in general form. You have observed that this inequality is not yet in general form because you have observed that the right side of our inequality is not 0. Okay, to make it 0, we need to transpose 1 on the other side of our inequality. So we have 2x over x plus 1 minus 1 is greater than or equal to 0. Then you have observed that the left side of our inequality, we have two expressions. We have the rational term and the constant term. So we need to combine these two terms to make it a single expression. Now, to make it single, we need to find the LCD first. Since there is only one denominator, which is x plus 1, so it is understood that the LCD is x plus 1. Then, since you already have the LCD, so LCD divided by the denominator of the rational term, so the result is 1, then you multiply to the numerator. So the result is 2x. Then, the constant term, you have observed that there is no denominator, or it is understood that the denominator is 1, so we can directly multiply x plus 1, or the LCD, to the constant term. So we have x plus 1 times negative 1, the result is negative times x plus 1. So we have now 2x minus times x plus 1 all over x plus 1 is greater than or equal to 0. Now, we will now express this into single expression. But before that, we need to distribute first the negative to the expression x plus 1. So we have negative times x, negative x. Negative times positive 1, we have negative 1. So we have now 2x minus 1 all over x plus 1. And combine like terms, since 2x minus x is x, then copy minus 1. So we have x minus 1 all over x plus 1 is greater than or equal to 0. Step number 2. Find the critical values. Set the numerator and denominator of the fraction equal to 0 to find the critical values. So since the numerator is x minus 1, so we will equate this to 0. Then find the value of x. So the value of x that will satisfy to the given equation is x is equal to 1. You have observed that we transpose negative 1 on the other side so that it will become positive 1. Then the denominator, since the denominator is x plus 1, so we will equate this to 0. Then transpose positive 1 on the other side. So we have x is equal to -1. So the critical values are -1 and +1, or +1 and -1. Step number 3. Plot the critical values in a real number line. Use open circle or closed circle depends on the inequality used for the numerator. Note, all the critical values of the denominator must be plotted in open circle. Since we already identified the critical values, which are -1 and +1, so we will now plot these critical values in a real number line. So let us start with -1. Since -1 is in the denominator, then we will use an open circle. Then we have also +1. Since 1 or +1 is in the numerator and the inequality is greater than or equal, then we will use a closed circle. Step number 4. Write the set notation form of each interval in a real number line. So you have observed that we already plotted the critical values in a real number line, and it divides the real number line into 3 intervals. The first interval, we have x is less than -1. You have observed that we use the inequality less than because that is an open circle in a real number line. It means that all values of x are less than -1. The values are from -infinity to -4, -3, and -2. So -1 is not included in the given interval. The next interval, we have the values -1 is less than x, but x is less than or equal to +1. Since you have observed that we have an open, then closed, therefore the open is less than, and the closed is less than or equal. It means that all values of x are greater than -1, but less than or equal to +1. The possible values or the values of x are 0 and +1. So there are 2 integers belong to this given set of values of x. Then the next interval, we have 1 is less than or equal to x, or it is just the same as x is greater than or equal to 1. It means that all values of x are greater than or equal to 1. So the values of x are 1 is included, 2, 3, 4, so on and so forth hanggang positive infinity. Step number 5. Test each interval using the value of x if it satisfies to the given inequality. If the value of x on the interval is true, then it is the solution set. Otherwise, if it is false, and then it is not a solution set. Again, we will not use the critical values as our testing values. So, let us now test each interval using the value of x if it satisfies to the given inequality. In the first interval, we have x is less than -1. It means that we can use any values of x as long as it is less than -1. So in my example, my testing value is -2. So I choose x is equal to -2. Then we will substitute this value of x to the given inequality. So substitute -2, we have 2 times -2 over -2 plus 1. Is it greater than or equal to 1? We do not know yet. Then, by simplifying the left side of our inequality, 2 times -2, we have -4 over -2 plus 1 which is negative 1. So we have negative 4 over negative 1. Is it greater than or equal to 1? Then simplify. We have negative 4 over negative 1 is positive 4. So which is greater than or equal to 1? And this is true. Then let's proceed to the next interval. It means that we can choose any values between negative 1 and positive 1. But you have observed that there are only two integers. We have 0 and positive 1. But take note, again, positive 1 is a critical value, so we cannot use positive 1. So in the second interval, the value of x as our testing value is 0. Then substitute to the given inequality. So we have 2 times 0 over 0 plus 1. Is it greater than or equal to 1? We do not know yet. So 2 times 0, we have 0 over 0 plus 1 is equal to 1. So 0 over 1, is it greater than or equal to 1? The result is 0 is greater than or equal to 1, which is false statement. So let us now proceed to the third inequality, which is 1 is less than or equal to x, or x is greater than or equal to 1. It means we can use all the values that is greater than 1 or equal to 1. But again, since positive 1 is a critical value, we cannot use that as our testing value. So in my example, I choose x is equal to positive 2. Then substitute to the given inequality. We have 2 times 2 over 2 plus 1. Is it greater than or equal to 1? We do not know yet. Then simplify 2 times 2. We have 4 over 2 plus 1 is equal to 3. And 4 over 3, is it greater than or equal to 1? Yes. So this statement is true. Therefore, we have now the following intervals that satisfy to the given inequality. Then, we will now write the set notation that satisfy to the rational inequality. If there are two or more sets that satisfy, use union or the word or to combine the solution sets. You have observed that the first interval is true, the second is false, the third is true. Therefore, the solution set is the set of x such that x is less than negative 1 or 1 is less than or equal to x. You have observed we combine the intervals that satisfy to the given inequality. Or you can also write in this form the set of x such that x is less than negative 1 or x is greater than or equal to 1. They are just the same. Let us now solve the inequality x minus 2 all over x plus 3 is less than 0. Step number 1, we need to write the given inequality in general form. You have observed that it is already in general form. We will now proceed to step number 2 to find the critical values of the given inequality. So we will start with the numerator. We will equate the numerator to 0. So x minus 2 is equal to 0 and the value of x is equal to positive 2. The denominator, we have x plus 3 is equal to 0 and the value of x is negative 3. The critical values are negative 3 and positive 2. Then, step number 3, we're going to plot the critical values in a real number line. So let us start with negative 3. So you have observed that negative 3 is the critical value of the denominator. It means that we will use an open circle. Then we have positive 2, which is the critical value of the numerator. Now, let's go back to the given inequality of what is the given inequality or symbol of inequality. You have observed that the given inequality is less than. So it means that we will use an open circle for our numerator. After this, we'll now proceed to step number 4. Then, we need to write the intervals in the given real number in the step 3. So, the first interval we have x is less than negative 3. And the second interval we have negative 3 is less than x, but x is less than positive 2. And the third interval we have 2 is less than x. Then, let us now proceed to step number 5. We're going to test if the given interval will satisfy to the given inequality. So, in the first interval, let x is equal to negative 5. Then substitute this to the given inequality. We have negative 5 minus 2 all over negative 5 plus 3 is less than 0. So, to check if this is true, we will now simplify the left side of our inequality. So, negative 5 minus 2, we have negative 7 over negative 5 plus 3, which is negative 2. So, negative 7 over negative 2, which is positive 7 over 2, which is less than 0. So, in this statement, this is what we call a false statement because positive is always greater than 0 and not less than to 0. So, this is a false statement. Then, the second interval, we will now choose 0 to make it easier for us. Then, substitute to the given inequality. So, 0 minus 2 all over 0 plus 3 is less than 0. So, we do not know yet. So, 0 minus 2, we have negative 2 over 0 plus 3, which is positive 3. So, we have negative 2 over 3 is less than 0. Of course, this statement is true because all negative values is always less than 0. Then, let us now proceed to the third interval. So, I choose or let x is equal to 3. Then, substitute to the given inequality. So, we have 3 minus 2 over 3 plus 3 is less than 0. We do not know yet if it is true or false. Then, we simplify 3 minus 2, which is positive 1, over 3 plus 3, which is 6. Then, 1 over 6 is less than 0, which is false because positive is always greater than 0. So, you have observed that there's only one interval that will satisfy to the given inequality. And this is now our step number 6, the solution set. So, always write the set of x such that just copy the interval negative 3 is less than x, but x is less than positive 2. And this is now the solution set.